Okay, so this second video is about still word problems. And I know that this first slide doesn't look like word problems, but we really are going to do some. But these word problems, if you notice, there's not going to be an equation with them. So that's why this lesson is called Writing Quadratic Models. So if we're given some information, we need to be able to write an equation so that we can use it. But I wanted to do this first one not in context, just to see if we remember how to write equations. So this is just a plain quadratic that opens up. Its vertex is at 3, 1. So hopefully if we think about vertex form, everybody should be comfortable at least writing this, right? That our vertex is at 3, 1, so we'd write -3 inside the parentheses, 1 outside. And the only thing we don't really know right now is our a value. And we can figure that out a couple of ways. One of the ways is to just use a different point on our graph. So here we've got a point at 4, 3. That's an x and a y. We can take that x, plug it in, take this y, plug it in. It would look something like this if we did that. And then we still have our a left, but that's our only variable now, so now we can solve for a. So if we weren't sure what the a value was, we can just plug in a different point than the vertex for x and y and solve for a. So that's what I did. Worked inside the parentheses, 4 minus 3 is 1. 1 squared is 1, so that's a 1a. And then to solve that, just subtract 1 from both sides. So we'd have 2 equals 1a, or really just 2 equals a. So then our equation, now that we know that a is 2, we can just go ahead and put that in the front. If we were using our brains a little bit more, we'd realize that this first stair step is a 2, and that's always a dead giveaway. That our a value is a 2, if you remember that from graphing. The first stair step size is always the a value. And then just to double check, our next stair step is a size 6, so those numbers were changing by 4, which is right, because remember our rate of change is double the a value. So we could have gotten that just directly from the graph, but sometimes when we work in our word problems, they're not going to be quite this perfect. So we do need a method for solving for a, and that method is just to plug in an extra point and then solve for a. Okay, so let's try that in some word problems. So this problem is about an archer who shoots an arrow, and it says that the arrow follows the parabolic path shown and hits the ground, and it hits the ground over at 90 feet. Oh, not 90 feet, 90 meters. I'm going to put that on there so I don't forget that this is meters and this is also in meters. All right, so if the arrow just went on, it would land 90 feet away. But then it says, if we had a 0.65 meter tall target and it was 77 meters away. So if we placed a target 77 feet away. So here's our target. We're counting by 10, so there's 70. So 77 is maybe about there. So if we placed a target 77 meters away, would the arrow hit it? So just kind of looking at this, 77 is about here, right? That's about 77. So on this arrow's path, it kind of looks like over at 77 that it might hit it, right? But we don't know for sure because we don't know the height when the distance is 77 feet away. We know that the target is 0.65 feet, but we don't know how high our arrow is. If we had an equation, we could just plug 77 in for x and see what we get out for y, and then we would know how high the arrow is. But we don't have an equation. Luckily, we know we can write one. Since we have the vertex, that should be very easy. I went ahead and plugged into vertex form there. So opposite of 18 is minus 18 inside, 1.6 outside. And then, so this is one of the ones where you can't really tell what that first stair step size is. So we are going to have to actually solve for the a value. So let's take another point. We have 2 to pick from. We could either use the y-intercept or the x-intercept. I wanted to avoid decimals, so I'm using the 0.90 that's on the path. And I'm taking the 90 and plugging it in for x, and the 0 and plugging it in for y. And then I can solve for a, right? So this is what it looks like, plugged in 90 for x and 0 for y. And again, we're going to solve for a, but we've got to work out all the rest. So 90 minus 18 is 72. 72 squared is 5,184. So we've got that in front of a. Then we just need to subtract the 1.6 over, and then divide, and that's a really ugly fraction. So we're just going to approximate with a decimal. So please know that our answers are not going to be perfect since we're approximating. Okay, so this is our a value. We can take that and plug it right in for a, and we'll have our full equation. And this is what our full equation will look like. Our a value and our vertex are in there. Okay, so our whole goal of this problem was to see how high is the arrow 77 feet out. So what we needed to do is take this x, 77, and plug it in and see what are we getting out. So that's what I did. Here's our equation. 77 is in for x. And when you plug that in and work it out, you get that the y value of that ordered pair is 0.5557. So at 77, we're about 0.56 feet high. So the arrow is only 0.56 high, but the target goes up to 0.65. So the arrow is definitely somewhere on that target. It's not in the middle of the target, but it is on the target since the arrow is lower than the height of the target. And that's what we want to know, right? The arrow is at 0.5557 meters above the ground, 77 meters from where it started. Therefore, if we put a target at 0.65 meters at 77 feet, then it would hit the target. Oh, not feet, meters. All right, so again, if we don't have an equation, sometimes we just have to write it so that we can use the equation to see where are our objects at certain points. So let's try another one. So this is the opening of a tunnel, and it says that there's been a graph that's been superimposed, and you can see the graph on top of it, where x and y are measured in feet. And we've got a semi-truck that's going to be driving through this tunnel. So here's my semi from the back, and it's going to be going through the tunnel. And what we want to know is basically, is it going to fit? So if you look, let's see, we're counting by 3. So 3, 6, 9, 12, 15, 18, 21, and 6, 9, 12, 15. If you look, our max height up here is 12, 15, right? Our vertex up there. But hopefully you're realizing that even though the highest point on this is 15, the truck's not 0 feet wide. It's not like it's okay that I know the truck's only 10 feet tall and that fits under 15, but the truck's kind of wide, so I don't really care about the vertex of this quadratic. I care about kind of the sides of the tunnel. Is the truck going to fit on the sides, or is the truck a little bit bigger, and maybe even though it fits underneath 15, it might hit over here on the edges. That would be bad, and that would be bad, right? So we need to figure out exactly how high the tunnel is at where the edges of the truck are. So let's think about that. The truck is 8 feet wide. So if the truck's kind of truck driver's using his brain. I'm going to make this smaller. We'll be optimistic. Ooh, let's make it a little bit smaller. We'll hope that it's going to fit. If the truck driver is kind of using his brain and he wants to be safe, he's going to drive right through the middle of the tunnel, right? And if his truck, it tells us, is 8 feet wide, that means 4 feet are going to be on each side of the middle of this tunnel. Remember, the middle of this tunnel is at 12. So 4 feet on each side of 12. That puts us over at, so if I go 4 feet over that way and 4 feet over this way, I'll be at 16. That's 4 feet past 12. And 8 is 4 feet before 12. So really what I want to know is, over at 16, what's this ordered pair? 16 comma what? And what's this ordered pair back at 8? They should be the same since this is a symmetric graph. But I want to know, how high is the tunnel 4 feet from the center, right? That way I know if the truck, hopefully that the tunnel is higher than 10 feet at those spots, so the truck would fit. So what I'd like to do is take 16 or 8 and plug it into an equation and see what the y value is that goes with it, but I don't have an equation. So we need to write one. We do have the vertex, so we could plug this right into vertex form and then solve for A like we did in the last two problems. But I want to stretch your brain a little bit and give you another method. We do also know that our intercepts are over here. We've got an intercept at 3 and an intercept at 21. So we can put that into factored form pretty easily. Instead of vertex form, put it into factored form, right? Isn't that factored form telling me that I have intercepts at +3 and +21? Because +3 and +21 are the two numbers that would make those parentheses equal to 0, right? And the only thing that's really missing for us is our A value. So we'll do it the same way as we were doing in the other ones. We need a point that's on this graph. So a point that's on this graph we already knew was 12, 15. So we'll just take that, plug the 12 in for both of the x's, and plug the 15 in for the y, and we can solve for A. And again, we'll be in factored form instead of vertex, but that's okay, we can still use that equation. So there I went ahead and plugged in x and plugged in y. And we'll just work this out. So 12 minus 3 in that first parentheses is 9. 12 minus 21 in the second one is -9. 9 times -9 is 81, -81. Divide that -81 away, and there is our A value. So it is ready to go back in for A, and then we'll have our full equation. And it looks like that. Again, it's in factored form instead of in vertex form, so it's a little bit different than the last two. But we can still work with it. It's still an equation where we can plug in x and see what we get out for y. All right, so come back to our picture. In our picture, our truck is in the middle of the tunnel. So 4 feet on each side of that middle part of the tunnel at 12, which remember we said puts us at 8 and 16. So we can either plug in 8 and figure out what our y value is, or plug in 16 and figure out what our y value is. It doesn't matter because they should be the same height since they're symmetric. So I chose 16, and here is my work for plugging in 16 for x. So here it is. And when I plug 16 in for x, put it all in my calculator, this is what I got out. So what we're finding is at these two spots, the tunnel, at 16, we are at about 12 feet, and at 8, we are at about 12 feet. So luckily, the tunnel is higher than our 10-foot tall truck. So our truck will fit under this tunnel. Except, we were kind of assuming that the truck has the option of going through the middle. But what if this is a 2-lane road? Well, that's not safe. You can't drive in the middle of the road. If it's a 2-lane road, this back of this truck, we have to be all the way over, right? So all 8 feet of that truck now needs to be to the right of 12. And if we're all 8 feet to the right of 12, that puts us over at 20. So if we're over at 20, now we are not very tall. And let's just double check, let's use our equation to see if we are over at 20 as our x, what is our y? How tall is the tunnel there? So I went ahead and did that, plugged in 20 for x, here it is. Put it all in my calculator, and I got out that the tunnel is only a little bit above 3 feet tall if we are 20 feet out. So if all of the truck is on one side of the tunnel, this is not going to work. So that's what I went ahead and wrote. I just wrote out both possibilities. If the road is a 1-lane road, then yes, the truck can fit under the bridge, because remember the bridge was 12 feet tall. Or if we were splitting and letting the truck go in the middle. But not if it's 2-lane road and the truck has to stay on one side. Then the bridge is not even close to tall enough for it to go under. Right? Okay, I'm going to stop this one so this video doesn't get too long and give you part 2 here in just a sec.